Morning, guys. So we're going to continue our review for the final exam. In this case here, we're going to look at topic 1, which is on quantitative chemistry, basically all the math that we learn in chemistry. Yes, this one here was our horrible Stoic test, but hopefully this time looking back at it, you're going to find topic by topic, the ideas weren't all that bad. The only thing that made it challenging first time through was maybe getting used to the vocabulary, getting used to some of the unit conversions. Hopefully having another look at it this time will be a little bit better. So let's just go through some of these calculations. So topic 1 here is on stoichiometric relationships. First thing that we introduced was different elements here actually had a different mass. So on your periodic table here, of all the elements I could have picked, I chose one element, which is carbon. Carbon happens to be a very stable element, a very common element in our universe. Carbon actually comes to us in different isotopes. We chose one form of carbon, that's specifically the carbon-12 form, and we came along and we said, let's pretend this carbon-12 atom is exactly 12 atomic mass units. It's always best to say no units because it's going to be relative to carbon-12 being 12. In the olden days, we used to say 12 AMU. Nowadays, typically we say 12U. Basically, what we're doing is we're just creating a unit. Because these masses are way too tiny, if I put these on a diagram scale or an electronic balance, this is not going to be nearly enough for a gram, so we need to put ourselves in the right order of magnitude, and how we did that was we said, the mass of carbon-12, let's just call that 12. Everything else on the periodic table is now going to be relative to that. So for example, hydrogen, also very tiny, but hydrogen, when it has the number 1.01 on our periodic table, because the number 1 is about 12 times smaller than 12 for carbon, we know hydrogen, even though I don't know exactly the grams of it, it's going to be 12 times roughly smaller than carbon-12. Let's compare it to magnesium. Magnesium is sitting right here. It has a molar mass of 24.3. Because 24 is roughly double of 12, I still have no clue what the mass of magnesium is, say in grams, but at least relative to carbon, magnesium is expected to be twice as heavy. So by defining the unit, by defining a right order of magnitude for carbon, we can now have all the other masses relative to carbon being 12, which is why you're going to see this phrase very often, relative to carbon-12, or even relative to 1/12, the mass of carbon-12. That's basically saying the same thing. If I had said carbon-12 is going to be 12, and I take 1/12 of that, 1/12 of 12 is just going to be one of these new units. So they give you a nice picture representation of this. Helium on our periodic table is quoted at a 4.00. If I put that on balance, if I make it relative to 1/12 carbon-12, each of these is going to be 1 atomic mass units. I need 4 of these units to actually counterbalance helium. So helium relative to 1/12 of carbon-12 has a mass of 4, and that's actually the number that we supply to helium as 4 on the periodic table. This was useful when we started looking at protons, neutrons, electrons in chapter 2. In this case here, nobody has the time to actually count individual atoms. We don't have scales that are sensitive enough to actually find the direct number of grams. So what we're going to do instead of dealing with individual particles like this, the number 12 was special for carbon-12. We're going to take our electronic balance. Remember, our periodic table weights the averages. That's why we have these decimals. But we knew this number 12.01 on the periodic table was special for carbon. And what we ended up doing was we actually ended up starting with the carbon-12 and actually putting carbon-12 atoms, many of them, all inside a box until we actually got back the number. Actually, this one here should actually be 12. We'll deal with the isotope aspect later on. So in this case here, we would assume that we have many carbon-12 atoms are necessary before we end up back at exactly 12 grams as we had from before. As you might remember here, the name for this container, this box full of chemicals, we refer to that as a mole. Inside a mole was an Avogadro number. This was our first conversion. 1 mole is going to be 6.02 times 10 to the 23. This number here is actually in your data booklet. In case you completely blank on your exam, you'll definitely find it there. I would type it in 6.02 EXP23. Remember, this one here is a 3 sig fig number. So especially when you're doing your rounding, this one here has also been rounded. If you Google it, it's 6.022 something. But most of our measurements are limited to 2 or 3 sig figs anyway, so keeping that to 3 sig figs is fine. Again, this mole here, the number is called Avogadro's constant. It was defined for carbon, but seeing as we have this number and seeing as everything else is going to be relative to carbon anyways, we then supplied, I can have an Avogadro number of carbon, sure, 6.02 times 10 to the 23 of carbon. I can borrow this number and I can say, what if I have 1 mole of hydrogen? Well, that means I have an Avogadro number of hydrogen. 1 mole of magnesium. Well, that means I have an Avogadro number of magnesium. So I'm borrowing that same number. I'm not redefining a new constant for every number. It was defined for carbon, and everything on a periodic table is relative to carbon. Now, for sure, even though these containers contain the exact same numbers of particles, whether they're atoms or even molecules, depending on my molar mass, on the periodic table, carbon weighs 12, and Avogadro number of carbon atoms will weigh 12 grams, whereas hydrogen, which we said was 12 times lighter, a box full, the same Avogadro number full of hydrogen atoms, each hydrogen atom is 12 times smaller, so the box of hydrogen, so this one here is going to be 1.0 grams, and similarly for magnesium here, magnesium is 24.3. The number of particles inside the box is always going to be Avogadro number, as defined from carbon, but depending on what chemical we're actually looking at, the molar mass would actually be different. Remember, it's always best on the periodic table to say no units, but in this case here, when we're dealing with molar mass, take whatever number. Again, here's where we weight the averages. Let's say for chlorine as an example, chlorine, it's given to us as 35.45. That 0.45 is to indicate that the chlorine 35 form is more common. But basically what's happening here is, let's say I'm given a handful of chlorine. Some of them are light 35, some of them are heavy. On average, when I just average it over, weight it by which one is more common, on average it's like every one of these particles is 34.45, and in this case here, grams per mole. For an Avogadro number of Cl, it's going to have 35.45. We know Cl is one of those diatomics, so actually when we do our molar mass, we'd actually double it, make it 70.10. So those are our 2 conversions so far. For carbon, 1 mole, the mole is this sort of box, it's a container. It always contains an Avogadro number. The other conversion is depending on what chemical we're looking at, we need to look at the PT, the periodic table, especially when the chemical is a little bit larger, we need to add up all the bits. So for example, let's take nickel chloride .6 water. Make sure you know how to name that. In this case here, nickel as a transition metal, I'd expect nickel 2 chloride, and then maybe a hexahydrate for that 6 water. When I'm adding up the masses, I know this as an ionic compound forms a lattice, but what we're going to do is we're going to add up what's the mass of nickel, we'll add twice the mass of chlorine, and then add up the mass of 6 waters. In total, that's going to be the molar mass, grams per mole. So when we do a conversion later on between mass and moles, I'm going to use that as the constant, which was derived on the periodic table. So those are the first 2 conversions. Our third conversion specifically had to do with gases. For gases are fairly nice because the kinetic molecular theory says they're already wildly separated, they're already traveling really, really quickly, they're sort of very expansive and spreading out through the container. Gases are going to respond really drastically to any changes in pressure and temperature. Remember, the volume that we're talking about in this point here is not actually the volume of the particle itself. What we're talking about is, even if the gases, like ideal gases, were point particles, we're talking about the volume of the balloon that we're actually sitting in, provided that we're at some temperature and some pressure. As I heat particles up, we're going to see this in the gas laws, as I heat particles up, the particles will start moving faster. If this is a stretchy balloon, by hitting the walls harder, the balloon here would actually expand, the size of the container would actually get bigger. Or I can change the pressure. Right now there's atmospheric pressure outside, it's trying to keep the balloon a certain size. I can bring this, say, underwater, and the water pressure would actually squeeze the balloon, assuming the balloon doesn't pop. I can also change the size of the balloon. The volume of a gas specifically, we say gases are compressible because they change really quickly and drastically with temperature and pressure. So only for a gas, we set up what's a nice reference feature. We're going to call it STP, standard temperature pressure. Make sure you know these 2 numbers here. The standard temperature in chapter 1 is 0 degrees. Everywhere else, from chapter 2 onwards to our chapter 9 redox and everything else, our standard temperature was 25 degrees. At least in chapter 1, our standard temperature is only 0 degrees. If I really wanted it to be 25, sometimes they call it RTP, room temperature pressure. Sometimes they also call it in your data booklet SATP. SATP is the standard ambient temperature pressure, and in that case, it might actually be 25 degrees. But at the very least here, for our conversions, when we used our 22.7, we were only at a standard temperature of 0 degrees. In the past, we used to use 1 atmosphere, 1 ATM, for the standard pressure reference. But ATM is like gradually losing ground here. ATM is a little bit over 100 kilopascals, whereas a bar is exactly 100 kilopascals. We're going to reset our reference. We could have really set our reference to be anything, 0 or 1 bar. In this case here, for this STP, you can be assured that 1 mole of any gas, right, because the gas volume only depends on the temperature and pressure. If the temperature and pressure are the same reference conditions, they're all going to be 22.7. So far, those are 3 conversions here. We're going to deal with this on the mind map, more so on the stoichiometry, just sort of summary there. Let's just keep going for now. The next section here was to look at percent composition, empirical, and molecular. Percent composition is exactly as it sounds. If I have a molecule, let's take CO2 as an example. CO2 by itself has a molar mass of 44. That's the total mass. But because CO2 here is made out of carbon bits and oxygen bits, I can ask you, what fraction of CO2 weighing 44, what fraction is just carbon? We're going to do percent composition. In some cases, we do volume for volume. In this case, we're actually always going to do it mass per mass. So all we're going to do is go to your periodic table. For carbon, it was quoted at 12.01. That would end up giving you a decimal. And this one here would be the fraction of carbon in my carbon dioxide molecule. Similarly, for a carbon dioxide, if I wanted to find the percent oxygen, I can take twice the mass of oxygen. This is sort of the brute force method. Or you can say, wait a second, this compound only contains C's and O's. If I knew some 25% of its carbon, I can also go 100 minus that 24, 25 to actually get the remaining part that's oxygen. You may be off by a little bit based on sig figs or based on a little bit of rounding, but depending on which way you do it, you should add up to roughly about 100. This is where IB is a little bit very technical when it gets to this kind of question. They want to ask you the empirical formula. They want to know what's the simplest whole number ratio of the compound given a particular percent composition, but they're not going to come up front and they're not going to give you, by the way, here's the percent carbon, here's the percent oxygen. They're actually going to usually word it as a combustion reaction. The reason why they like combustions is because they can actually, for a combustion reaction, we see that the carbons and the oxygens end up in totally different places. So let me just sort of draft out a question for you. Let's say I have a hydrocarbon or even like a sugar that actually has an oxygen. It might be told I start off with 2 grams of this sugar. I burn this sugar and I actually find out how much CO2 and how much water I get. I'm totally making up numbers here. Let's say I get 5 grams of CO2 and I get 8 grams of water. All right. So in this case here, because I am interested in the empirical formula, I'm interested in the x, y, z as a ratio, I'm actually not able to do any balancing at this point. But if you backtrack here, the whole notion of balancing is just to make sure that mass is conserved. If you look at this one here, where does all the carbon go? Assuming a complete combustion, you'll notice the C part all gets separated into the CO2. So regardless later on what the coefficient ends up being, we can actually figure out if I know 5 grams of carbon dioxide was produced, I can actually take what's the fraction of carbon in carbon dioxide, I can multiply it by 5 grams, which is the molar mass of the entire CO2, and I can figure out how many true grams of carbon do I have, because all that carbon would have had to have come from my carbon in the sugar. In a similar fashion here, we can do for the hydrogen, so HY, upon burning it, it just ends up what fraction of the water is hydrogen. All the hydrogen would have had to come from this H. You might imagine oxygen could be done the same way. Well, oxygen, some of it goes here, some of it goes here. The problem with oxygen is during a combustion, they may or may not explicitly tell you this, but for a combustion, we know we're reacting it with excess oxygen. So the hard part in trying to find the oxygen that we care about in the sugar is we're actually getting other oxygen sources come in. That extra oxygen is actually amounting why this mass is actually heavier than the sugar to begin with. In that situation here, what I would do, instead of worrying about the oxygen that actually comes into play, we're going to take the 2 grams of sugar, assuming that you found how many grams carbon, how many grams hydrogen. I can just take the 2 grams minus off those 2 bits, and that'll actually give you the oxygen. At that point, there was a little work to get to these numbers, but if you remember for your empirical formula stuff, we end up dividing out the mass. Let's put them all on a level playing field. To start simplifying the numbers, I then ended up dividing out the smallest number. Depending on your numbers, I want to keep the rounding as minimal as possible, but sometimes the rounding might end with, let's say, a 0.5. I might scale everything up by 2. If it's like a third, 0.33 or 0.67, I can scale it up by 3s. 0.25 or 0.75, I can scale it up by 4. I want to basically not round in one chemical to skew the ratio. I want to scale everything so that we have simplest whole number ratios. I would encourage you to keep extra decimals. You can be a little sloppy with suffix going through, because at the end of the day, we get whole numbers anyways. Make sure it is simplified at the very end. Remember, the empirical formula here has been simplified. My real compound may be some scaled up version. The key idea here is, because your empirical unit sort of acts like your Lego block, your molar mass is going to be some whole number multiple of that molar mass. Sometimes the real compound is just, it's exactly the empirical formula. Sometimes it's double as big. Sometimes it's 5 times as big. At this point, this really should be a whole number. If you're still getting like a 1.33 or 1.5, something went wrong with your empirical formula calculation. So that's a nice review of percent composition, empirical molecular. The next section here, we're looking at our gas laws. They do say we don't need to know necessarily the names of the individual gas laws, Boyle's law, Charles's law, Gay-Lussac's law, because what we've done is we've actually combined these formulas into this, what's called combined gas equation. This one here, for some reason, is not in your data booklet, so please memorize this combined gas equation. And basically, you'll know to use this formula. It's a comparison between your starting conditions. This is condition 1, and you're either changing temperature and pressure, asking what is the new volume. There is a notable before and after. There's a condition 1 and a condition 2. Because we are just setting up a ratio, here's just a comment on units here. Pressure and volume can be any units. Let's say pressure was atmosphere. As long as it's also atmosphere on this side, you're fine. Let's say volume was crazy and it was on centimeters cubed. As long as you use centimeters on this side, it's fine. As long as the units are the same on both sides, fine. However, for all three of these laws, they were testing it at absolute temperature. The temperature must be in Kelvin. If the question asks you for the final answer in Celsius, convert it to Kelvin first. Do the math in Kelvin. Once you have the Kelvin as a final temperature, then convert it back to Celsius. The conversion there is just rescaling by 273. You can do 273.15 if you like. Right? So that's one equation we do for gas laws. The other equation here, we don't have a notable before and after. We just have, here's the pressure, here's the volume, here's the temperature, what's the moles. We're not actually changing anything. I'm just interested in finding what's the missing unknown. So in this case here, because we don't have a condition 1, condition 2, we're not just setting up a ratio. Your best bet is to put everything back in SI units. Pressure should be in pascals, the volume should be in meter cube, temperature we set already in Kelvin, and molar masses are going to be grams per mole. In this case here, there will be a few conversions for you to memorize. On your data booklet, they do remind you that volumes are sort of off by thousands, but what they say is 1 liter is equivalent to a decimeter cube, and they say, by the way, a meter cube is 10 to the negative 3. Right? I need to divide by 1,000 to get that way. I need to multiply 10 to the 3 to get to centimeter cube. What I've just done for you listed here is, let's imagine instead I have 1 of the meter cube. Meter cube is equivalent to a kiloliter. I multiply by 1,000. I don't need to show that conversion cubed, that conversion 3 times. I know it's off by 1,000 to get to liters, and it's off by another 1,000 to get to centimeter cube, which is equivalent to a milliliter. So that's how you do it for volume. For pressure, we typically want to go back to just straight old pascals. I know in chemistry we typically like doing kilopascals as well. It turns out that if I try to do like a pressure times volume, technically the SI units were supposed to be a pascal times a meter cube. Those were our SI units. It actually corresponds to if I had a kilopascal corresponding with a decimeter cube. Because if you look at this one here, going from pascal to kilopascal, I would end up dividing by 1,000. Like we just mentioned, meter cube and liter are also off by 1,000. These two thousands would cancel out. So as long as you have kilopascal and as long as you match it up with decimeter cube, that's fine. Or you just go straight to your SI units, pascal and meter cube. I would technically go back to SI units, but chemists tend to like just leaving kilopascals. 1 bar is 100 kilopascals, and atmosphere is 101.3 kilopascals, whichever you're more familiar with. We do call this the ideal gas law, meaning a gas in a perfect world. In the nature of science section, they might ask you, what makes a gas ideal? What assumptions are we making for gases to actually behave this way? In this case here, the assumptions seem a little crazy. There's two assumptions. One is the fact that the particle, the grouping itself, actually has no volume. So imagine my real gas actually has some size and shape. It may get intertwined and mangled together. We're going to pretend for a second that I erased all that volume that the particle has, and let's treat them as point particles. They're just tiny little X's, and basically because they don't have any shape anymore, they're just going to more easily collide with one another, collide with the walls of the container. The other one, also seeming like a crazy assumption here, is we're going to assume that there's negligible attraction. We're going to assume that they basically don't know each other present. And yet in chapter 4, we've done intermolecular forces. We've done, well, protons are always positive. We have negatives on the outside. No doubt there's going to be some London forces, maybe even dipole-dipole forces in between. What we're pretending for an ideal gas is we're pretending these intermolecular forces are not there anymore. They essentially have no idea each other present except for the occasional bounce. In this case here, what we want to do, when does a real gas behave like an ideal gas? What you want to ask yourself is, do I want a big container or a small container for my real gas to look like this ideal case? In this case here, our ideal gas formula will be best if your separation is actually big. If I'm in a really, really large container, even if I have size and shape, even if I do have those London forces, we knew in chapter 3, our London forces get weaker by the time the radius actually increases. So if I'm big separation, my real gas actually follows ideal behavior, such as why I put down here, it actually deviates from ideal behavior when we're actually in small separation. When we're in a tight confined space, the size and shape of my real gas, those London forces will actually become more important. That's when my real gas doesn't quite behave as ideally. Turns out our Pivnert formula, this ideal gas formula, actually is a really good first approximation. You can look up some van der Waals correction terms if you go on into chemistry, but this one here actually doesn't, it's actually a fairly good assumption, even at sort of everyday separations. So let's continue onwards in our review in chapter 1 here. On the back side, we're looking at solution chemistry. Solutions can be any mixtures, one state dissolved in another state. Pretty much what we did is we dissolve solids into liquids. Although the solids themselves actually do take up some volume, we're going to imagine that they're so fully dispersed, so fully dissolved, soluble, that it actually doesn't change the volume of the overall liquid, and overall the solvent is going to be called the solution once I've dissolved the solid inside. So if I had, let's say I was making orange juice, I start off with water, which is no molarity. I start dropping in maybe orange juice powder here. As that orange juice powder here starts dissolving inside, again, we're going to assume that solids themselves just fill in the gaps left behind by the solvent. If the overall volume doesn't change, we can define a concept called concentration, and concentration is going to define for me how much solute is there for a given volume of solution. Few different units that we use for concentration. If I was doing this sort of kitchen chemistry here, I might just measure how many grams of powder and figure out how many liters based on maybe a measuring cup or some sort. I can do grams per liter. Again, IB doesn't like using liter, so instead of using liters, it uses decimeter cube, especially when I put it just sort of with those negative exponents. Gram, the negative means per, gram per decimeter cube. If I have the unit as gram per liter and I want to get it into the more useful mole per liter form, this implies that I need to know the molar mass, because what I'm going to need to do is I need to cancel out the grams and go to moles. This is how you interconvert between concentration with grams or concentration in molarity. In regular Chem 12, this is what we would call molarity, and then we would use molar as a unit, capital M. Let's say 1.5 molar means you have 1.5 moles for every given liter. Remember, this is an intensive quantity. It doesn't mean that you have to necessarily have a liter. It says pretend I have a liter of exactly the solution. It would be like I have 1.5 inside. So this becomes a nice concentration factor. Be careful when we do this conversion here. This is the only conversion where the 1 is actually with the liters. If you think back to molar mass, we were grams per 1 mole. For Avogadro's number, it was 6.02 per 1 mole. For molar volume, it's 22.7 liters per 1 mole. This is the one time that the constant is actually going to be the size of the container, which is 1 liter, and we're actually figuring out how many moles have we dissolved into the solution here. So there's molarity there. Again, IB doesn't like using moles per liter, so they would rather say 1.5 mole per dm cubed, so moles per liter. Questions will definitely be worded in moles per decimeter cubed, but you're more than welcome to leave your answer in even capital M or mole per liter. You can express it in either way because they're equivalent. We did a side note here, especially when concentrations got to be really tiny. I didn't necessarily want to keep numbers with a lot of times 10 to the negative, a whole bunch. So sometimes what we did is parts per million, or by extension, parts per trillion, parts per billion. Basically what we're doing is we're setting up a ratio. This one here, I think of it as a percentage. You know how percent we go, take my fraction and I multiply it by 100. In this case here, even 100 isn't big enough for a scaling factor for parts per million. I'm taking a really tiny fraction, and I actually need to scale it up by 1,000,000, or if it's parts per trillion, I times it by 1,000,000,000. I basically scale it up until this ppm number is actually a little bit larger. So that's concentration in general there. For concentration, you do want to be really careful. Once your particles are dissolved, there's no grabbing out. Let's say I overshoot the molarity. There's no taking a pair of tweezers and grabbing those particles back out. The only way then to change concentration is then to dilute. Remember, for a dilution and mixing question, we're going to rely on the fact that we started off with some moles in a liter. We already had some concentration. Then the amount of moles here is going to be C1 times V1. That actually counts the individual number of particles. No matter whether I add water to it or whether I evaporate off of the water, I assume that the pins, or I assume that the chemicals themselves are unchanged. If you look at your formula, C is N over V. I just rearrange that there. So the N, C1 times V1, counts it before. It also has to equal to C2 times V2. It counts it afterwards. So we're relying on the fact here that the moles remain constant to actually do our dilution problem. We typically start off with a stock solution that's really, really concentrated, really, really dangerous to work with. You add water to it to dilute it down. The orange juice would get less strong tasting, less concentrated by doing so. A mixing question is essentially two dilutions in one. I'm just going to color code this here. Imagine I have a blue solution, and imagine I mix in a green solution. For a dilution problem, the easy question is the volume just adds up. The volume of the blue adds to the volume of the green. So the total volume is now actually going to be bigger. But what we're going to be assuming here is all those X particles are now swimming in a bigger pool. All those O particles are swimming in an extra pool. I would do a C1V1, C2V2 just for the blue side. I would do a C1V1, C2V2 just for the green side, where the V2 is actually the total volume in this container. Both solutions have been diluted, so that both molarities should have dropped, and then we can finish off with the dissociation afterwards. Here's some definitions for you here. We didn't do solubility as a separate chapter, but some things that are good for you to note. Things that are soluble, we said they dissolve well, so the state of matter is aqueous. If something is low soluble or doesn't dissolve really well, we're going to leave it as a solid. We saw that yesterday with our net ionic equations. This is where we got our pink sheet. You don't have to memorize it, but there are some general trends that I would just, it's good to keep handy. So for example here, things that are always soluble, we mentioned yesterday, pretty much the alkalis, the +1 salts, as well as any nitrates are always going to be soluble. So let's say I need silver ions in solution. I'm never ever going to get a bottle of just pure silver ion. That's charged, that's unstable. But what I can reach for is I can reach for a bottle that's AgNO3. You'll say, where did the NO3 come from? I just know nitrates are always soluble. So the second that this ionic compound, typically a solid, the second that this hits water, I give it a stir and mix, I wouldn't be surprised for this silver nitrate to break up. This is called the dissociation. This is when water rips up the ionic compound, and basically I get the silver ions that I need. The nitrates will just stick around as spectators. In a similar fashion for your, if I need some, let's say I need phosphate in the solution, again, I'm not going to have a bottle of just pure phosphate. I can reach for like lithium phosphate. Well, where did the lithium come from? It could have been any alkali salt, just like before. By dissociating, sure, extra lithiums are just going to sit there and they're not going to do anything, but we're going to actually have the phosphate that we need for the solution. Make sure for a dissociation, or what's called an ionization equation, make sure you do show off the charges. And although water is good enough to break apart the positive and negative, we learned in chapter 5 it can actually stabilize the different charge bits. It's not good enough to actually break apart the covalent compound. So keep your polyatomics together. As you look at this double replacement example, I gave you one example on the last lesson with formula equations, working your way up to net equations. Maybe just take this question, try writing, checking your pink sheet, or not even, if you can memorize it there, try writing the ionic and see if you can get back this overall equation. Finally, in chapter 1, we put it all together with stoichiometry. Essentially, the notion here is we're going to bring back that whole notion of coefficients in the balance equation. For a recipe, mass has to be conserved. All the numbers have to be accounted for. If I was 2 Li's before, I have to have 2 Li's afterwards. Hopefully by now you've gotten a lot of practice with balancing. Remember, IB likes wording it, once you balance it, they're going to ask you it as sum of the coefficients. Add up all the numbers. Remember to add up the numbers that are 1. So for example, let's take the Haber process, N2 and H2. You can ask yourself, what's the catalyst for this? So NH3. Okay. You can check whether it's balanced or not here by inspection. Nope, these are odd numbers. I might need to double that. I might need to 3 this. If I then ask you sum of the coefficients, don't tell me 5. Remember, even though there is that 1 that I don't write down, remember this one here still has a 1. So sum of the coefficients on this left-hand side is 4. Sum of all the coefficients is 6. You just add them up. The other way they can word it is just left to right. They might just say choice A, B, C, D. They might just say in that order 1, 3, 2. But majority of the time they ask you the sum of the coefficients. These coefficients here, the 1, 3, and the 2, they give you what's referred to as the mole ratio. They help you link numbers of A to numbers of B. And once you have that, you can link all your, well, we did molar mass to moles. We did number of atoms to moles. We did 22.7 to get to moles, even for concentration to get to moles. We use this mole ratio to jump chemicals, and then we're back to using the same 22.7 molar mass and all that. Okay. This mole ratio will work whenever we're comparing numbers of particles. So whether we're comparing just plain old, even if I went straight from molecules to molecules, your mole ratio would work. Moles to moles, your mole ratio would work. There's something we call Avogadro's hypothesis. Because for gases, their volumes only depend on your temperature and pressure, as long as there's no mention that temperature and pressure change. Even though for other volumes, they don't follow the mole ratio, if we're specifically volume of gas, let's say I was 10 liters of N2, as long as we're at the same temperature pressure, it doesn't even need to be STP, but as long as the temperature and the pressure don't change, 10 liters of N2, I can predict it's going to be 30 liters of H2, and I can predict it's going to be 20 liters of NH3. So Avogadro's hypothesis actually gives you a nice connection here. If you tried out your math, it would be sort of like if we were at STP, we would have had to divide 22.7, but we would have multiplied the 22.7 to cancel out. It's like the volumes also follow the same mole ratio as the balance equation. So this part here is Avogadro's hypothesis, right? And that gives you a nice shortcut there, so you don't need to show a lot of work for the divide 22.7 times 22.7. The other spin-off of this question here was a limiting and excess style question. Basically, when I give you both amounts, let's say I have N2 and H2 becoming 2NH3. Let's say I gave you this one here was 10 grams, and the other one was 5.0 times 10 to the 24 molecules. I totally made up these numbers. Anytime I give you information for both, there's a good chance that one of these will actually run out first. Pretend we're making those s'mores again. Once we run out of one chemical, your production stops. You can't actually create any more chemical. Our strategy was to go to the same unit, but assuming from both. So let's start off. Let's assume the 10 grams was limiting. Assume that the N2 runs out first. That would mean I'm going to figure out, let's say I was trying to find molecules. Actually, no, let's do moles of NH3. It could be any unit, depends on the question. 10 grams, I'm just going to draft it out for you here. N2 is diatomic, so N is 14, so 2 times it is 28 grams per mole. The mole ratio tells you for every 1 part N2, there's 2 parts NH3. I figured out that number there. Let's assume the H2 is limiting instead. The thing here is I want to go to the same unit of the same chemical to actually figure out which one ran out first. So I take this molecule, use your EXP notation, 5 times 10 to the 24. This is molecule. I'm going to use Avogadro's number to get rid of molecules and go to moles. And then through the mole ratio, I can go 3 parts H2 to 2 parts NH3. Remember, we don't want to double count any coefficients, so the coefficients will only enter this mole ratio step. Okay. So that way I don't accidentally triple the molar mass or times 3 the Avogadro's number. The coefficients will only enter this mole ratio step. Whichever number here is smaller is going to be the one that ran out first. So the chemical that was limiting is the ingredient. So let me just actually type these numbers in since I have them. 10 divided by 28 times 2. I can produce 0.714 moles of my NH3. 5E24 divide Avogadro's times 2 over 3. This can produce 5.53. Okay. There's no telling that these numbers have to be very similar. I just totally popped these numbers off my head here. In this case here, the smaller number is going to be what's produced. Give me some concluding statement. Usually I say then, based on these numbers, therefore the 10 grams that N2 ran out, N2 is then called the limiting reagent. Reagent is a fancy word for reactant. And then they might ask you how many moles was formed. It's just going to be the smaller number. I started off with no moles of NH3. By the time I produce 0.714 moles of NH3, the N2 has cut out. The production stops. I can't make any more product. I'll leave it up to you to try to find the excess. Remember, there's two ways of doing that. Either you do the subtraction first. You figure out 5.53 minus off 0.714. I could have made an extra 4.82 moles of NH3, and you calculate back how much of the H2 is sitting around waiting to make that. Or what you can do is you can start off with the limiting, start off with the 10 grams, figure out, instead of jumping from N2 over to NH2 like we did, figure out by the time the 10 grams get used up, how many molecules of the H2 has it actually consumed away, and then I take the 5 times 10 to the 24 minus off what you calculate there. Both ways, give or take a little bit of sig figs, should give you the same number. That's your excess. We also just sort of finished off with a little bit of a percent yield. Basically, all these calculations, all these conversions we've been doing have been assuming that we're in a perfect world, assuming the reaction 100% goes to completion. We've seen this Haber process here is actually settles into equilibrium. It doesn't all go fully forwards. There may be a whole host of errors, random errors, systematic errors. There can be impurities and side reactions, all saying that even though the calculation should have produced an ideal, a perfect amount of 0.714, typically your actual amount, which I can't predict, typically your actual is actually going to be less than your theoretical yield, less than what we calculate. So the theoretical yield here, this was by calculation. I should have gotten 0.714 in my question. Maybe I was told, oh, I only got 0.526. That number had to be given to me. I can't, based on your skills as a chemist, actually calculate what that number would have been. And I basically scale it up by 100, randomly take those numbers, 0.526 divided by 0.714, gives me a decimal times 100. Do your significant figures, so I'm getting 73.7%. So out of the 100%, out of the 0.714 that I was supposed to get, I only got 73%. If this was you, I would just track down some of your procedures, see if there's any errors. You can sort of make some improvements in your design to try to up this percentage to try to get more bang for your buck. One last thing to go over as we just finish off chapter 1 is the notion of a titration. This is the one where we drop the base here. It doesn't necessarily have to be base in the burette, although most of our titrations we've done base here, acid in the Erlenmeyer. We use an Erlenmeyer because we're going to need to swirl this. Okay, I don't want it to be splashing over. For a titration, we basically want to set this up so that there's actually no excess. We want to drop the base so slowly or so precisely that I may have an unknown amount of acid at this point, but I drop the base, basically drop-wise here. I want the base to essentially have exactly killed off the H+, and maybe that extra OH- here can no longer find H+. I want to stop there, that there's no excess. You've done many titrations by now. If you end up overshooting, oh no, the phenolphthalein, the indicator actually changes to a pink color, you'd have to reset, okay? But we're looking really precisely when this is a really pale pink color. Remember, for our phenolphthalein, I'm going to shorthand it PHP. It was in acid, it was colorless. It didn't show any color. In base, it actually showed a pink color. We're actually looking for what's called the endpoint of the indicator. The endpoint is when it actually changes color. So we're looking for a pale pink between the two of them. If I used another indicator, let's say it changed from blue to yellow, I think the in-between is a green color. So you're looking for that intermediate color. The whole notion of this one here, we can read from the burette what's the difference in volume. For one of the concentrations I have to know, so for our lab I think we use 0.10 moles of base. Although for the acid it was an unknown amount, a question mark molarity of the acid, it's totally up to you how much you decide to test. Most of our pipettes have been 10 mils, every now and then we did 25 mils. Yes, in some sense, by dropping in the base, we actually screw up the total volume. But remember, we never actually measure the final volume in this Erlenmeyer anyways. I know once we've actually counted the H+, that H+ was only originally sitting in 10 milliliters. Sure, I've destroyed the sample, but I just take the moles that I calculate divided by the 10, and I now have the concentration of the entire, not only the concentration of what I tested, but the concentration of the stock container that I have. In this case here, this one here, we did a lot more in Chem 12, but basically this is because we have to know one molarity. The question is, how can I know this molarity so precisely that I can use it to find an unknown molarity? You might endlessly go, oh, let's do another titration. Let's pretend we have our unknown base, right? Let's say it's an unknown molarity base, and let's titrate it with the acid where I know the molarity. Maybe this is 0.20 molar acid. But then you end up in this sort of chicken and egg kind of question here. Well, how would I then know the concentration of the acid instead? To solve this problem here, we're going to start off with what's called a primary standard. I always think of a primary standard as a solid. There are only a few chemicals that actually fit the bill for this one here. A primary standard has to be super pure. It can't absorb extra water or react with things in the atmosphere, so that, especially as a solid, NaOH is not a really good primary standard, because NaOH, even if you leave it exposed for an hour or so, it's actually absorbs some of the moisture. In our lab, we use oxalic acid. Chemically speaking, oxalic acid really keeps to itself. So when you measure out a mass, let's say I measure out 1.50 grams, I'm fairly confident that the entire 1.50 grams is actually oxalic acid. I then dissolve it to make a standardized solution. My standardized solution is going to be a solution where I know the concentration very well. And with that, I basically have a concentration I know very well. I use that to standardize. I'm using that as a verb. Standardize means to find the molarity. Use my standard solution that I know the concentration, standardize my base. The NaOH wasn't a good primary standard, but once it was standardized, once I know the molarity, I can then use that for other future titrations to find the concentrations of other chemicals. So those are just some more sort of qualitative aspects of a titration. Pretty much we did the limiting excess kind of style question, but for a titration problem, we don't want any excess. So in a nutshell, that's chapter 1 for you there. If you have any questions, feel free to let us know, and we'll go from there. Thanks, guys. Take care.